All right, we're recording. Good. So 5.4, if you notice, the section is called sinusoids. And sinusoids itself is a very interesting word, right? Sinusoids. It almost sounds like something you would go to the allergist for, and he'd have to have surgery to go and remove your sinusoids so you can breathe better, right? Or is that just me? That would be sinusoid. Okay, good. All right, so we're off to a great start. Sinusoids. What is the key word in sinusoids? Is it so? Oids. I like it. You didn't say I. There's no I in sinusoids. There's actually two I's in sinusoids. 5.4, yeah. No, it's the first part, which is what? Sine. So a sinusoid is a function that is closely related to the graph of sine. And so what we're going to do today is we're going to learn what the graph of the sine function looks like on the Cartesian plane, which means we're going to unwrap it from the unit circle, all right? So to do that, we have a T-chart here that I provided you, which if you remember back in Algebra 1, a T-chart was the first way that you had for graphing functions. If you had the equation of the function, you would choose arbitrary values for x, which is going to be our theta. And of course, we could choose those to be anything we want because that represents the what variable of our function? The x values? Independent variables, right? So we can choose them to be anything we want independently. But the outputs, of course, depend upon the input. So that's what we call the y values, the dependent variable. So once we fill in this T-chart, we're going to have ourselves some x values and some y values that we can then plot on the Cartesian plane, thereby unwrapping the unit circle. So before we start filling in this chart, remember that the sine ratio represents what? Well, it represents the y value on the unit circle. But in general, a trig ratio, I told you never to forget to remember that a trig ratio gives you 2 of 3 sides of a what? A right triangle. Yeah, and so the sine measures the what of that triangle? The y value, which is the height. Good. So the sine measures the height. Sine, y, height. Remember that? So we're going to be plotting for all these different independent values of theta the height of these reference triangles as we rotate around the unit circle from 0 to 2 pi. That's what we're going to do. Now, what are the units in the left column? What are the units of theta here? Radians, which means that the units are actually what? Unitless. Good. So if we're looking at physical applications that involve distances or lengths of the sine function or any of the 6 functions, later on we'll get to all of them, we have to use a unitless measure on the x-axis. So we can then assign whatever arbitrary units we want to it. So that's why we have to use radians. What would the units of our y column be once we fill it in? What are the units of sine of theta? There's no units, right? Because again, it represents a ratio of 2 of 3 sides of a right triangle. And if the triangle did have units, it would be like feet divided by feet. What happens? They divide out. So when you use radians, you always have a unitless input. The sine, cosine, tangent, secant, all those 6 trig ratios, they're already unitless. So our x and y axis are going to have no units at all. All right, so help me fill in this T-chart. What is sine of 0? 0. Sine of pi 6? 1/2. Sine of pi halves? 1. Sine of 5 pi 6? 1/2. Sine of pi? 0. Sine of 7 pi 6? Negative 1/2. Sine of 3 pi halves? Negative 1. Sine of 11 pi 6? Negative 1/2. And then coming around full circle to 2 pi, sine of 2 pi is 0. We're back where we started. That's once around the unit circle. Okay? So I chose pi 6 instead of pi thirds because they had what? Relatively nice ratio values as opposed to the ones that had the radicals. Okay, so what we have now is we have a set of ordered pairs, 0, 0, pi 6, 1/2, pi halves 1. And we can now plot those on the Cartesian plane. So let's do that. Come over here, and we will draw an x and y axis. So there's my y-axis. You can use the snap feature. And my x-axis, snap it in place right there. There we go. All right, so what we want to do is we want to set the table. You always set the table before you eat, and boy, we're going to eat. So I'm going to come out some arbitrary distance here that is not quite all the way. I'm going to come about halfway, and I'm just going to call that 2 pi. All right. Now, once I've called that 2 pi, I can eyeball the halfway point. Hey, welcome back, band. And what's half of 2 pi? 1 pi. We just downloaded 5.4. And then halfway between 0, which is the y-axis, and pi, we'll cut that in half and call it pi halves. So now we have pi halves pi. We can bisect the distance between pi and 2 pi and label it as what? It would be 3 pi halves. Good. Come in late, still contribute. Nice. So these, including 0, those are very special angles. On the unit circle, those are our what angles? They land on the axis, thereby dividing the quadrants. They're called the quadrantal angles. Okay? Now, those are kind of the important ones because those hit the x and y axis. But I also gave you the pi 6 angles in there just so we have some more points. So pi 6 is going to be somewhere closer to 0 than the midpoint. It's going to be to the left of the midpoint. So that'll be pi 6. So you could draw that kind of arbitrarily. But once you have this distance set up from the y-axis to pi 6, we downloaded 5.4 and we're on example 1. Then that distance between 0 and pi 6 you want to kind of preserve. So now if you back off of pi by about the same amount, that is going to be 5 pi 6. And then if you go the same distance on the other side of pi, you get 7 pi 6. And then that same distance just in front of 2 pi, we'll call 11 pi 6. All right, so your pi 6 angles are always closer to 0 and pi than the midpoint. Good morning. We're on 5.4. All right, so that sets up the x-axis. Now to set up the y-axis, look at what all the values of sine range from in our Tchart there. They all fall between what two values? What's the smallest value in the chart? -1, and the largest value? 1. And we know that the sine values always have to be between -1 and 1 because it's a measure of one of the short sides to the hypotenuse, which is the longest side. So it can't be outside of 1 or -1. So let's come up about a little more than halfway, arbitrarily call that 1. And now that same distance, we'll come down here and call that -1. So now we have set up the x-axis to accept our ordered pairs. So now we pick our favorite flavor. I'm going to choose burnt orange because I don't like my oranges unless they're well done. And I'm going to choose kind of a beefier point because we're going to put dots, okay? So let's go ahead and plot these points. 0, 0, right? Whoa, that's too big. Oh, golly. Okay, there we go. 0, 0. That's perfect. Now, what is sine of pi 6? 1/2. So notice this is important about the graph of sine and how it increases. Pi 6 is only 1/3 of the way to pi halves, or 90 degrees. But in 1/3 of the distance to its maximum value of 1, it's already covered half of the vertical space. Okay? So at pi 6, 1/3 of the way out, it's already halfway between 0 and 1. Maybe I'll scooch it down just a smidgen. You're just eyeballing it. Okay, good. Now at pi halves, what's sine of pi halves? 1. So we'll put a dot there. Sine of 5 pi 6 is back to 1/2. So now you want to try and match it up with the height of the other one over there. Sine of pi, back to 0. So notice what happens to our sine values. As we rotate through the first two quadrants, sine, which measures the height, it starts at 0. The heights of the triangles increase to a maximum at pi halves of 1, and now they're decreasing back down to 0 at pi. And then from pi to 2 pi, we're just rotating now to the two quadrants where sine is negative. So 7 pi 6 is going to be -1/2. 3 pi halves is -1. 11 pi 6 is back to -1/2. 2 pi comes around full circle to 0. And congratulations, you have now given your coordinate plane a bad case of the measles. So in Algebra 1, when you were first drawing your functions, once you put a sufficient number of points on the coordinate grid, what did you do next? Connect them. So I'm going to make it a little bit smaller. Now, when you grew up, you had those little activity books, and you had all these connect the dot features, and they were numbered in a random order. So if you want to connect the dots in a random order here, that's fine. If you do that, it should make an elephant when you're done. Or not. Okay? That's not how we connect dots on the coordinate plane, right? We always connect them how? from left to right. Good. So as much fun as that was, that's not how we do it. Okay, so here we go. Are we going to connect them with straight lines? No. If this were a scatter plot, your calculator has a feature that connects them with straight lines. But there are infinitely many values in between these angles that we did not choose, and they have sine values. The sine values increase and decrease through a continuum. Okay, as you rotate from 0 to pi halves, the heights of your triangles gradually increase, passing through all the possible triangles in between. So you want to connect this not with straight lines, but rather with nice, smooth curves. All right, smooth. And you can kind of do it in quarter cycle intervals, like from 0 to pi halves, and then from pi halves back down to pi, then from pi down to 3 pi halves, and 3 pi halves back up to 2 pi. And look how beautimous that is. There you have what we call one cycle of the graph of sine. One cycle. What does cycle imply? That there are more cycles? And the second cycle would be maybe from 2 pi to what? 4 pi. Well, if I rotate around the unit circle from 2 pi to 4 pi, and I stop at the same places, the angles are different, right? They'll be different. But they will be what with these angles? Coterminal. Excellent. And so what do we know about coterminal angles? They have the exact same trig ratios. So what do you think the graph would look like from 2 pi to 4 pi? The same as this, all right? So this graph repeats itself in regular intervals of 2 pi. In regular intervals of 2 pi, which makes perfect sense because that's once around the unit circle. So look what we could do then with notability. We can lasso this graph, and we can copy it. And if I want, I can come over here past 2 pi and just paste it and kind of line it up. Now the numbers are the only thing that are going to be different. So if you want to erase those numbers, that would be fine. But the values match up with the coterminal angles. Okay? So that would be then what the graph of sine looks like from 2 pi to 4 pi. Well, what do you think the graph would look like from 4 pi to 6 pi? Same. If you want to paste it back down, just add another cycle, we call it, over here. Now mine goes off the paper, but that's fine. It continues on out there. And of course, what if I went backwards? What if I looked at the graph from negative 2 pi to 0? I'm still going around the same unit circle, right? So they should be the same values. Okay, so if you want to paste one last one here and just line it up. There you go, that looks good. Again, the numbers will be different, but the graph, the sine values will be exactly the same at the coterminal angles. And we can continue this, what? How long? Till we run out of room? Or indefinitely. So if I had the x-axis, if I worked in the sine factory, the S-I-N-E factory, not the S-I-G-N factory, and I worked on the assembly line, and the assembly line just went by at a constant rate, and my job was to make this graph all day long, I wouldn't sit there and trace it. I would make a stamp. And as the assembly line went by, I would just go stamp, 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 stamp. Kind of like what we just did with the cut and paste. My graph then, my stamp would have to be how wide? How many radians? 2 pi. Perfect. Okay? So that every 2 pi when it came by, I would just stamp, stamp. I would really enjoy my job. It'd be easy. I'd be good at it. Okay? It'd be real easy. And I would do that every day, all day long, and then I'd hit stop on the assembly line. I'd go home, come back the next day, hit start stamping again. What a wonderful job. Okay? Because this graph repeats itself every 2 pi, we call this function in general a periodic function. It belongs to a larger family of functions called periodic function. So what's the key word in periodic? Period. Good. This class is called second period. How often does second period occur, minus the weekends? Once a day. So every 24 hours, second period happens again. Every 24 hours. Okay? Just like the graph of sine, it comes around periodically. Not every 24 hours, but it repeats itself every 2 pi. International Polar Bear Day is a periodic holiday. How often does it come around? Once a year, once every 365 days. Periodic function, okay? Rolls around at a regular interval. Just like the guy that rolls by my window there about every 10 minutes. He's just the same guy. He just periodically walks by. He's roaming the halls. There he goes again. Every 10 minutes, the periodic wanderer. So things that happen as periodic functions occur at regular intervals, all right? Occur, or reoccur, I should say. Reoccur at regular intervals. We then define the period of this function to be the length of one cycle. The length of a single cycle. That is the smallest distance in time or in radians that it takes for this thing to repeat itself. So the period of International Polar Bear Day is 365 days. The period of second period is every 24 hours. What is the period then of our sine function? 2 pi. So we call the period P for period. Makes sense? And it's 2 pi radians. So what that means then, of course, is that sine of theta is equal to sine of theta plus 2 pi. Theta plus 2 pi. Right? That's the smallest distance where the values start to repeat themselves. And again, it makes perfect sense because 2 pi radians is how far around the unit circle? Once. And then the cycle starts all over again, like the water cycle, right? The circle of life. All right, sweet. So this is a periodic function. But there are many, many types of periodic functions. And we need periodic functions to model things in the real world that happen periodically. Just like we have quadratic functions to model types of natural phenomena. We have exponential functions to model like population growth. We even have log functions that model what? We had all kinds of problems with logs, didn't we? Boy, did we. But some of those problems we were able to evaluate and figure out when we had applications of logs. Like, what? Carbon fixation? Carbonation? Carbon dating. Yeah, carbon dating would be more like exponential. You could do a modified logistic to it. Sound intensity, light intensity, earthquake intensity. There are lots of things you can model with log functions. But a lot of those, polynomial, exponential, logs, rational functions, they're insufficient for modeling real-life behaviors that exhibit this type of behavior, right? This would be periodic behavior. What are some things then, either from science class or from your experience, that you know can be modeled by a periodic function such as this? What? Waves, yeah. In fact, waves are so common, whether in the physical world, physical waves, like water waves, exhibit periodic functions. The tide rolls in, the tide rolls out. You have the ebb tide, the neap tide, the ebb tide, the neap tide. So the height of the waves over time can be expressed as a periodic function. Sound waves actually travel through the physical medium we call air as what? As wave functions, yeah. So I don't know if in science class you've ever used the oscilloscope, have you? You should demand it. There's probably an app for an oscilloscope. But if you speak into it, you can actually see what your voice looks like. And it resembles some type of sine wave. It can be modified, okay? And we'll talk about that here in a second. Light waves, microwaves, they all exhibit periodic behavior, okay, in their physical form. But there are other things in the world that we can model with periodic functions. Hand widths? Hand waves? Oh, yeah, they go back and forth. Or even if it's a person that does this, bye-bye, right? The height of their hand open and close, I guess? Yeah. How about like Comal County Fair? Y'all went to the Comal County Fair? You rode the Ferris wheel, right? It's the scariest ride there. Only because you don't know if the bolts are tight. That's what makes it scary. You can model your height above ground as a periodic function, right? You hit a low point, and then you hit a high point. Then you come back down to a low point and a high point. So you can model anything that rotates, whether it's the distance on a Ferris wheel, or you know a rock that's in your tire as you drive to school, right? The height of the rock above ground, or just your camshaft as it spins, your pistons go up and down. You can model anything that occurs at regular intervals using a periodic function. Okay, pretty powerful. Simple harmonic motion. Have y'all heard of that in science class? Simple harmonic motion. Hooke's law. No? If you take a spring and you suspend it from a board, and you neglect those two things we call gravity and air resistance, just throw them out the window. If you then start that in motion by either stretching or compressing the spring and letting it go, unless it's acted upon by another force, that spring with the weight attached to it is going to continue to oscillate above and below. We call that simple harmonic motion, because the restoring force that brings it back up to its equilibrium is always directly proportional to the displacement from that equilibrium. And so they work in harmony with each other. So you can model anything with simple harmonic motion using a sine wave. Okay? Now, go ahead.
Why is it the periodic table?
Does the periodic table repeat at regular intervals? No, but there are properties as you go from left to right that repeat. So that's why they call it periodic. Like you have the alkali earth metals and the halogens. Their atomic mass increases, but when they lined up, now they're in this column, they exhibit that periodic common trait. That's why they call it periodic. That's a great question, because themselves, the elements don't repeat, but their properties do. Okay, good question. Is that the right answer? That sounded good. Yeah. I knew I got my minor in chemistry for something. It was for that question right there. Yes, money well spent. Okay. There are lots of periodic functions. You could draw anything that happens at regular intervals, but when it happens so smoothly like this is a special type of periodic function we call a sinusoid. Okay? A sinusoid. And there are going to be two sinusoidal functions. The first one, of course, is sine, and the second one you'll just have to use your imagination. It's one of the other remaining 5 trig functions. We'll get to that. Oh, you already think you know. I think you're right. All right. Sinusoids, then, is going to be a graph of a sine function or another one. Probably not cotangent. All right. So let me show you what we're doing then when we unwrap the unit circle. Here's kind of a nice picture that shows the relation between where you are in the unit circle as you rotate and the wave height. But there's another nice visual on the Desmos calculator. Some of y'all might have the Desmos app. Here is the Desmos website, and you can find things that are already pre-programmed. So here is the unit circle. We're starting right here at 0 on radians, and we're starting at 0 right here. Now, if I hit start, you'll see it rotate, and you'll see it map out or trace out the sine value as we go from left to right. This is unwrapping the unit circle. Here we go. This is where you go, ooh, ah, ooh, ah. See, so we're coming back down, approaching pi, where sine hits 0 again. Now we're in quadrant 3, where the sine values are negative. The height is increasing in the negative direction to 3 pi halves, where we collapse it down to nothing. And then it hits 2 pi over here, and we come full circle. And then it traces backwards. Ooh! Now notice the graph continues on. 2 pi to 4 pi, there's my stamp. 4 pi to 6 pi, stamp, 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 all the way left and right. And we can even go into negative land. So it just makes perfect sense that because the circle repeats itself every 2 pi, so do the y values. All right? So that's kind of a neat little animation there. But it's not critical for your understanding. Okay, so what we're going to do now is we're going to learn some physical names that are uniquely associated with sinusoids. Okay, stuff that we've seen in the past, but they have special names. First of all, if you graph it over its period, we call that again the cycle of a graph. One cycle of the graph is graphing it over the length of its period. This is the graph of sine, and the first thing I'm going to do is I'm going to give you a mnemonic that will help you sketch it, because this is going to become now a parent function, and we're going to be sketching transformations of it. So just like you can quickly sketch e to the x now without looking, or ln of x, or x squared, or x cubed, you're going to have to do that with sine. So sine, first of all, starts at 0, 0. So it starts on the x-axis. And then it increases at pi halves to a high point, then back down to an axis. Then at 3 pi halves, it gets to a low point, and it completes one cycle back at 2 pi by finishing on the axis. So those quadrantal angles, 0 pi halves pi, 3 pi halves, and 2 pi, I call the critical values for sine. Critical in the sense that they're all you need to sketch one cycle. So notice we start on the axis, then we go high, then axis, then low, and then axis. And that's one cycle. So you need 5 critical values for one cycle. So sine goes axis high, axis low, axis. Axis high, axis low, axis for sine. And to help you remember that, there's an easy mnemonic that I created for you to remember that. I went to school with someone named Kahala. She was a good friend. Since then, I've fallen out of touch with Kahala. It was like 25 years ago. But I've been really good friends with Sahala over that time. And I hope Sahala becomes one of your close friends as well. So who is Sahala? And what is Sahala? No? You don't have room in your heart for another friend? Sahala wants to be your friend. What does Sahala stand for? The S in Sahala stands for Superman. No. Sine. Good. And it's axis high, axis low, axis. There you go. Sahala is a way to help you remember how to sketch one cycle of sine. Sahala, sine, axis high, axis low, axis. Done. And then you can repeat the process indefinitely to get more cycles, right? So what would it be after that? Low axis, high axis, low. That would be Sahala Hal. That might be her middle name, Sahala Hal. I don't know. Okay. Sahala, that's all you need to know. Now, because it is a sine wave, there are certain things associated with it, okay? The first thing I want to define, the period is shown, but the center line, the Freon is recycling, the center line that runs right through the middle of the graph horizontally, which we're calling the axis, isn't always the x-axis, but it is always called the sinusoidal axis. The sinusoidal axis. You have to say it like Curly Howard from the Three Stooges. Not really. Do y'all even know who that is? Curly, Moe, and Larry? Oh, they're great. And sometimes Shemp when Curly wasn't there. He didn't have curly hair. He was bald, actually. Curly Howard was bald. But that's how he talks. Slightly. So it's sinusoidal. It's the sinusoidal axis. And when we look at transformations of this, it might move up and down. But it's always going to be the center line that runs through the center of the graph. Now, when you measure the wave height from the sinusoidal axis, that is the distance from the axis to the high, or the distance from the axis to the low, what do you call that in your science class? The wave height. The amplitude. So we're going to call that A for amplitude. And it is the wave height. Okay? If you think about a sound wave, this could represent some note. Okay? If you simply increase the amplitude of that sine wave, it's just going to make it taller. The axis points stay the same, but you're stretching it vertically. What does that do to the note when you increase its amplitude? If that sound wave represents, let's say, a middle C, then increasing the amplitude of the sound wave would increase the, not pitch, the volume. It increases the volume. Very good. Because there is a device that helps you remember this. Anyone ever heard of an amplitudifier? Like for a guitar, an amplitudifier? Sometimes called just an amplifier. Sometimes just called an amp. Yeah. What is the amplitudifier, or amp as you called it? What does that do to the sound? Makes it louder. So it's the same root. Amplitude, amplifier, amplitudifier. Okay? It makes the note louder. All right, the other thing is the period, of course, which is shown here from axis to the second axis point. You measure that differently in a science class. You typically measure it from high point to high point, or as y'all called it, crest to crest, instead of Colgate to Colgate. Or from trough to trough, right? Trough to trough. Y'all called that the what? When you measure the distance from crest to crest, you called it y'all called that the wavelength, which is related to frequency. And the wavelength has a cool letter. It's that one there, the lowercase Greek letter. What is it? Lambda. Guess what? Scientists and mathematicians, we like to do the same kind of work, but we like to call it different things. It just makes us feel more special. So scientists call the distance from height to height, or low point to low point the wavelength. But is that any different than the period? How far is it from pi halves to 5 pi halves? That would be where the next height is. How far is it from pi halves to 5 pi halves? Well, what's 5 pi halves minus pi halves? 4 pi halves or 2 pi. That's what we call the what? The period. So the wavelength is exactly the same as the period. They are mathematically interchangeable. Mathematicians use period. Scientists use wavelength. Exactly the same thing. It's the length of one cycle. And you can measure it between any two coterminal angles on the graph, and you'll figure it out. Any two consecutive coterminal angles, I should say. Now, you said frequency, Tate. Frequency is closely related to wavelength. What are some units of frequency? Hertz are the units that are commonly used, but hertz are a combination unit, like a Newton is a kilogram meter per second. Another way to measure frequency in its rawest form is in this fashion: cycles per unit of time, or radians. Cycles per radian. So what you do is you establish a fixed unit of time, or a fixed distance like 2 pi, and you count how many full cycles happen in that interval. Okay? Period is a little bit different. Period and wavelength, the units are this. It's going to be radians, or time, per one cycle. So if you're looking for the period, you don't care how many occur in a certain time. What you're interested in is how long does it take to make one cycle. So think about the units. Radians per cycle for period versus cycles per radians for frequency. How are those units related? Reciprocals. Yeah, they're reciprocals. So exactly the same way the units are related are exactly the same way the period and the frequency are related. Period and frequency are reciprocals of each other. So the period is 1 over lambda. I'm sorry. It's 1 over f. I'm getting my variables confused. The period is 1 over f, which is the same thing as lambda. Frequency and wavelength, or frequency and period, are reciprocals of each other. But the period and the lambda are exactly the same. All right? We're going to measure period simply because the frequency could be very, very high or very, very low. And so it might affect our graph. I want you to always be able to sketch at least one cycle, stretch it out, and clearly label it. Okay, so if you change the frequency of the graph, you're essentially not going to be stretching it vertically or compressing it vertically. You're going to be doing what? Horizontally stretching or compressing, okay? And when you change the frequency or the period of a sound wave, that's what changes the what? When you change the frequency of the note, you change the note itself. You change the pitch, right? So the frequency affects the pitch, and the amplitude affects the loudness of it, okay? So let's go ahead and look at the standard transformation form of sine of x. Now, first thing, notice that it's in function form now. It's f of x. F of x. So it's a function. We have an independent variable and a dependent variable. The independent variable for functions, we typically use x. But in this case, x, the independent variable, represents a what? An angle. Good. In radians, it's a unitless measure of rotation. So we're going to get away from theta now, and we're going to start using x. But in this context, because it's sine of x, x still represents an angle in radians. And the f of x represents the sine values, the heights of these reference triangles. Okay? So here it is in standard transformation form. We have f of x equals a times sine of b parentheses x minus c plus d. So just like before when we studied transformations exhaustively, the a, b, c, and d affect the sine equation and graph in the exact same way they affect any other equation and graph. So in general, when you multiply a function out in front by a, what does it do to the graph? Vertically stretches or compresses it by a factor of a. And of course, if A is negative, it also does what? Flips it across the, like x squared and negative x squared. It's the x-axis reflection. So it still does that. When you stretch or compress the graph of sine, you're affecting the sine wave height, which is the amplitude. So if you come over here, the absolute value of A then, in the case that A is negative, is called the amplitude. It still affects the graph the same way. What is the default amplitude then for sine? What number is by default in front of sine of x? 1. So guess what the default amplitude for sine is? 1. It goes up 1, then down 1. Up 1, then down 1 from 0. But if you doubled the height of the sine wave by putting a 2 in front, now the graph is twice as tall, and now the amplitude is 2. It goes up to 2 and down to negative 2. Good. Now the B, remember B always does what to the graph of any function when you multiply by x? Horizontal stretch or compress, right? Like Alex Meissner, who's playing tonight with the band and tomorrow with the Brontex, if you want to go. When's the band? 6 o'clock tonight? 7 tonight in the gymnasium or the auditorium? In the gym, okay? Get your tickets. So when he plays his accordion, he stands in one spot. Well, that's very rare. He doesn't usually stand in one spot. But let's say we nailed him to the floor temporarily. He can't move. When he stretches and compresses those bellows, what happens to the ribs in the bellows? They get further apart and closer together, but it stays the same. So that's what B does. It stretches and compresses horizontally. That will affect the what of the graph when you stretch it and compress it? The pitch, which we know is affected by the frequency slash wavelength slash period, right? So that will affect the period. But B itself tells you something unique for a sine wave. The absolute value gives you, because B could be negative, it gives you the number of cycles in 2 pi. B does not give you the period. It affects the period, but what it does give you is the number of cycles in 2 pi. What's the default value of B in regular old sine of x? It's sine of 1 times x. Yeah. So the B value is 1 by default, which means that the regular old sine function has how many cycles in 2 pi? 1. 1 cycle in 2 pi. That actually gives you the frequency. Okay? 1 cycle per 2 pi gives you the frequency. All right? Now C is going to be your horizontal shift still. But for a sound wave or a sine wave, we call the horizontal shift something very different. One of the things you can measure with a sinusoidal function is the phases of the moon. I took a moon selfie recently, right? Some of y'all did. Some of y'all did. And you caught the moon in one of its phases, right? Well, the phases ebb and flow, okay? New moon, full moon, crescent moon, gibbous, wax, wane, whatever. They come and go. So depending on where you are, when you take a picture, you catch the moon in a certain phase. You catch the graph of sine at a certain point. We call that a certain phase. If you play 2 sounds side by side with each other, and they sound, there's like a dissonant sound to it, those 2 sounds that you play, we say are out of phase with each other, okay? When 2 sound waves do not sync up properly, you get a dissonant sound. We say they're out of phase with each other. So we call the horizontal shift for a sine wave a phase shift. It's still a horizontal shift, but we call it a phase shift, okay? And then, of course, D is still the vertical shift, moves the graph up and down, but that's going to change what important feature on this graph? Remember that center line that runs right through the middle that starts off at y equals 0? If you have a phase shift, it moves the entire graph up or down. That center horizontal line becomes your frame of reference. That moves your sinusoidal axis up or down D units. So D now becomes the new vertical location of that sinusoidal axis. Okay, now, if the period is the length of one cycle, and B is going to stretch or compress it, the number of cycles in 2 pi, how can we figure out what the period is by knowing what B is? If B is the number of cycles always in 2 pi, and the period is the length of the cycle, what if B were 2? What happened to the period? If now I'm seeing 2 full cycles between 0 and 2 pi, the period used to be 2 pi, but now I have to see 2, so what happened to the period? it's half as big. So it's 2 pi divided by 2, or pi units. What if b were 4? Now from 0 to 2 pi, I see 4 full cycles. Instead of the original 1, what's the length of each one? It should be a fourth of what it used to be, which was what? 2 pi. So in general, the way you find the period from a standard transformation form is you take your old period of 2 pi and you divide it by the number of full cycles you expect to see in 2 pi, right? It makes sense. You have a distance you're working with 2 pi, and you want to divide it evenly into b pieces. You do 2 pi divided by b, and that gives you the length of each piece, okay? So here's the holy grail conversion between b, which you get from the equation, and the period p, which you need for the graph. Okay, so now that we have kind of the nomenclature figured out, let's go ahead and jump down to example 2. Because ultimately what you need to know at the end of today is how to sketch one cycle of sine, all right? Or, as I'm going to start referring to her, Sahala, okay? Sahala. So let's go ahead and sketch one cycle of Sahala. Here's what you're going to do every time. Y-axis, x-axis. What's the period for sine, Sahala? 2 pi. So come out an arbitrary distance, call that 2 pi. Bisect it, call that pi. Bisect that distance again and call it pi halves. So again, your 2 pi is arbitrary, but when you cut it in half twice, now you get your quarter cycle counting interval. The distance from 0 to pi halves should be preserved. So if you bisect now one more time, the distance between pi and 2 pi, that'll be 3 pi halves. And of course, there's 0. So now you have your 5 critical values, and they should be equally spaced, right? Because we did it by the bisection method. Now let's set the vertical axis, 1 and -1. So that's setting the table. That's setting the table, as I said earlier. Now before we eat, we have to put the food on the table. So let's put the food on the table. This is the Sahala method. S is for sine, right? So here we go. Axis, high, axis, low, axis. There you go. There's the food on the table. You don't need to put the pi 6 or pi thirds in there. Axis high, axis low, axis. Now it's time to eat. How do we eat? We connect the dots. Yum, 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 yum. There you go. Now notice how I connected? With smooth lines, yes, but you almost want to connect the dots with a quarter cycle sweep, okay? From 0 to 2 pi, it's increasing and concave down, we say, curving down like a frown. From pi halves to pi, it's decreasing, concave down. You actually have the curvature changing here on the axis. It goes from a frown to a smile, all right? So now it's decreasing, concave up like a cup, we say, and then increasing, concave up like a cup. All right, so it takes a little bit of practice. You should try and force the curvature to be frowning and then smiling, and it changes at pi. There's one cycle of sine. And if you needed more points, guess what you could do? You could simply keep that quarter cycle distance, which on your paper is this distance here, and you could just start throwing down more little hash marks that are roughly that same distance away. And if you needed more points, no problem. Where would the next one be? Just keep the pattern going. It would be high, then axis, then low, then axis. And you could just keep doing that in either direction if you wanted, right? And of course, all you have to do to label them is you're counting by what? How far apart are each of my critical values? Pi halves. So 1 pi halves, 2 pi halves, 3 pi halves, 4 pi halves. That would be 5 pi halves, 6 pi halves, 7 pi halves, 8 pi halves, and you can simplify as you go. Okay? So that is my goal for you today, to be able to sketch one cycle of Sahala like that with the correct values labeled. The high point and the low point, 1 and -1, and your 5 critical values, 0, pi halves, pi, 3 pi halves, and 2 pi, one cycle. Okay? Tomorrow we'll look at that graph, and we'll talk about some of the characteristics that we did for the other functions, like increasing, decreasing, local max, local min, symmetry, blah, blah, blah. Okay? So today you met Sahala, and tomorrow you meet her twin sister, fraternal twin. Fraternal twin. The other sinusoidal function, which Sarah already guessed is cosine. But she has a nickname. She has a nickname. It's not Kahala. That was my old high school friend. You'll have to wait tomorrow to meet her, unless you want to read ahead. All right. Have a great day. We'll see y'all back.